Hello everyone, my name is Mike. I have 10 techniques that I'm going to share with you for improving your group delay measurements on frequency converting devices that have embedded local oscillators. So I mean devices such as this MyTech satellite block down converter, which takes a 20 gigahertz input signal and down converts it to about 1 gigahertz using an embedded local oscillator operating at 18.75 gigahertz. So I want to measure the group delay of a device like this, and I'm going to share with you 10 techniques for making that measurement as easy and accurate as possible. And of course, I'm going to use a Rohde Schwarz ZNA vector network analyzer for making this measurement. We introduced this instrument about 1 year ago, and it has been optimized for making measurements on frequency converting devices such as this. And in particular, I'm going to use option K9. This is our two-tone technique for making group delay measurements on frequency converting devices. For more information on that option, please refer to application note 1EZ81. This application note covers everything you want to know about option K9 in making group delay measurements. But in this series of videos, I'm going through the optimizations one by one on the different parameters that we can modify in order to make the measurement as accurate as possible. Each video has its own idea, and okay, let's go. This is video number 6, and in this video I'm going to optimize the averaging setting that we use during the measurement. Not only am I going to optimize it, I want to explain why it's important to use averaging and when it's the most valuable. So in particular, consider the fact that we have to calibrate our channel before we can make measurements on our device under test. If we calibrate without averaging and there's noise present in the system, then that noise is going to be built into our error correction model. Once it's in the error correction model, it will be there forever, and it will be replicated onto our measurement results every time we make a measurement of a device under test. So I have to stress, if you can only average at one point in time, the best time to average is during the calibration of your channel. This gets rid of the noise as much as possible when we create the error model, and then we benefit from that every single time we make a measurement on the device. Now, of course, if we can average during the measurement of the device under test, that also has benefits. But if I could only do one or the other, then there is no doubt I want to average during calibration. Now, in the previous videos, we've already covered, let's automate the measurement so it's repeatable, consistent, and documented. Let's pick the optimal way to combine the two tones. Let's optimize the power levels. Let's optimize the tone spacing. Okay, let's optimize the resolution bandwidth. So now we're all the way to idea of optimizing how many averages we use. So I'm going to repeat what I did in the previous video and use a script to set up the instrument with 4 different channels, each channel having a different number of averages so that we can see directly the effect as we go through the different options that we have. Okay, let's go to it. Start from preset condition on the instrument. Going to launch that GPIB command explorer just like I did in all the other videos, and I'm going to select or open the script file that says number 6, let's use averaging. This is going to create 4 different channels, and it asks me to connect the calibration mixer so it can calibrate the 4 channels. This is the best way to do it. It's fair. Every channel has the same settings except for the averaging parameter, so we can really do an apples to apples comparison across the 4 channels. Now, the last channel I have set for 32 averages, so it's a bit slower than the others, and you can definitely see that in the response as we go through the calibration. But now that we're done, we can take a close look at what we've got, and we can decide what's the best averaging setting for our particular conditions. So again, I have 4 channels. This first channel has no averaging at all, and we can confirm that by going to the average setting while we cycle through the channels. So this first channel has no averaging. This is what we have been using up to now. We have not done any averaging up to now, so this should replicate the results we had at the end of our last video. And if we look at the peak-to-peak variation, we have about 100 picoseconds of variation with no averaging. Okay, that's how far we've gotten with all the other optimizations that we've made. Now, if we did just 3 averages, which if you watch this sweep, it sweeps very quickly, just 3 averages takes that peak-to-peak variation down to about 60 picoseconds. So a nice improvement for not much effort. And in this third channel, we go to 10 averages, and this takes the peak-to-peak down to about 30 35 picoseconds. Again, a solid improvement. And the fourth channel with 32 averages, which takes quite a bit longer to sweep, takes the peak to peak down to 16 picoseconds. So we can see already that our ability to tolerate noise can be traded off with how long we want to spend making the measurement. Just like with the resolution bandwidth filter, the narrower the bandwidth, the lower the noise, but the longer the measurement takes. Using averages is a correlated effect. Using more averages is effectively the same as using a narrower resolution bandwidth filter. But I like averaging a lot because I can see the results on the screen as we converge to the setting we're getting to. So I prefer averaging over a narrower bandwidth filter where the trace just goes really slow. And as I said, the other advantage of averaging is I can turn it on during calibration. So I can spend a lot of time averaging during calibration, and then during the measurement, I can turn the averaging off and get quick results. So I get the real benefit of building an error model with less noise, and then I can tolerate the noise during the measurement of the DUT if I need to make faster measurements. So this is why I really like averaging. So based on this, I'm going to select an averaging factor of 3 going forward. So I'm not going to go for the home run. I'm just going to take 3, which gets my peak-to-peak variation down to about 50 picoseconds. And I'm going to use that as I consider optimizing the next settings. And that's right. We're going to take this 50 picoseconds and we're going to push it down even more so that we get an even smoother trace at the end of calibration. We are not done yet. I have 10 ideas for improving this measurement, and this is only idea number 6. So keep watching.